Hey everybody, different setting for today. I am actually at home. I don't worry, I'm not sick. My son was a maybe apparently potentially exposed, but he is doing more than fine. So I have a hunch it's just a very precautionary request. So anyway, I'm home today, but that's okay. We'll get through the remainder of 2.6 here as best I can from my bedroom. Um, but let's keep going then. So yesterday we left off here. We're going to talk about resonance. So we did all these Lewis diagrams. We did the formal charge, and again, just to reiterate, formal charge is a better way of analyzing whether the structure that we've made is more stable than the octet rule, right? So the octet rule is great; it works most of the time, but formal charge will sometimes be a better indicator of a structure. All right, so that brings us to a topic called resonance. We're going to start the exact same way, okay? So I would like you to pause the video and draw out a Lewis diagram for nitrate, NO3 1 minus, if you could, or at least get started, okay? Try to get as far as you can, and if it starts getting a little confusing or something feels a little off, that's fine, but give it a shot. Why don't you try that right now? All right, so assuming that you've maybe tried something, what I want to do then, I'm going to try my best here to just obviously type things out because I don't have my smartboard features, which is a little sad, but that's right. So we have a grand total of, let's see, oxygen has 6 valence electrons, right? Times 3 is 18, plus nitrogen's 5 gives us 23, plus the -1 charge gives us 24. So we've got 24 electrons to work with, and let's start drawing out this structure. I'm going to put nitrogen in the middle. I'm going to just kind of surround this with 3 oxygens. These are pretty far away, but that's okay. This is way more clunky than if I were just here. We'll live. All right. We need a bond, right? So I'm going to make a bond between my nitrogen and my 3 oxygens, at least one for each. What that does then is now I'm subtracting off 6 electrons. I am now down to 18 to go. And I can simply just add these all the way around the outside. So let's do it this way. All right, you know what? I'm going to pause this and orient these so they look nice. All right, I've added all of my electrons now. So I'll subtract those off here, -18, and we're left with 0. Good, that's exactly what we want, right? So let me just move these around a little bit so they're a little nicer looking. Perfect. Okay, so at this point in time, right, we would do an analysis. We would kind of analyze where we're at. The octet rule, again, is pretty good, but we also need to make sure that the formal charge is minimized. So let's look at formal charge, okay? I'm going to switch color just for the sake of contrast. If I do the formal charge of we'll do the oxygens first, so the outer one. So this calculation right here is going to be for oxygen. Oxygen has 6 valence electrons minus 1, 2, 3, 4, 5, 6, 7 dots and dashes. In other words, we have a 1 minus formal charge on all 3 of our oxygens. Oof, that's not great. All right, let's do the next one. Formal charge of the nitrogen in the middle. 5 valence electrons minus 1, 2, 3 dots and dashes. Also, not great, right? So currently, the way that we have this structured, the way we have the electrons arranged, we have a -1 on all of our oxygens. We have a +2 on our nitrogen. That's not good. We don't want these to be 0, right? The other thing you'll notice is that the octet rule here for nitrogen is messed up. We only have 6 electrons, so that could be another indicator that we could maybe use to help us out. Okay, so this is unlike any example we've ever done, all right? This is unique. What I have to point out, and this is really, really important here, is that elements in the second row, oh man, I can't say it, will never expand the octet rule. Okay, what I mean by that is that if you have an element from row 2 off of the periodic table, okay, and nitrogen is in row 2, boron, carbon, nitrogen, is that right? Did I miss one? I don't have my periodic table next to me. Boron, carbon, nitrogen, oxygen, fluorine, neon, none of these will ever go beyond 8 electrons. They cannot expand their octet. This is different, right? Yesterday we had a bunch of elements that could. sulfur and iodine and the bromine here and the xenon over here. So there's a whole bunch of elements that can go beyond 8 electrons. But these are bigger atoms, okay? Elements from row 2, like nitrogen in this example, are just too small. They can't have more than 8 around them. So the octet rule must be followed on elements from row 2 off the periodic table. So that limits what we can do here. In an ideal world, if you notice, right, so this is the nitrogen right now is +2, the oxygen is 1 minus. In an ideal world, if we could, it would be great, sorry about that, it would be great if we could make a double bond here. Try to make that in. Well, that's not too bad. And then if we could make a second double bond. So if we could make a second double bond, that would allow us to fix all of the formal charges. Okay, and if you did the formal charge calculation right now, I'm going to just do it in my head, and I hope you can follow with me, right? These oxygens, the 2 oxygens on the bottom, 6 valence electrons, minus 1, 2, 3, 4, 5, 6 dots and dashes. That's a 0. That's good. The nitrogen in the middle, 5 valence electrons, minus 1, 2, 3, 4, 5 bonds. Also 0. That would be great. The oxygen up top, 6 valence electrons minus 7 dots and dashes. So it would still have a 1 minus charge. But remember, that's okay because we wanted to have the 1 minus charge because our molecule has a 1 minus charge. So it should be somewhere, right? But the problem with this structure that I've just drawn is that we can't expand the octet rule for nitrogen. We have 10 electrons by nitrogen right now. We're not allowed to do that. It's not going to work. So we have to go back one step and return this to the way it was. This is the correct structure of nitrate, the polyatomic ion. Now, there's another issue, okay? And this is what's going to lead us to resonance. And I'm going to put brackets around this thing, clunky brackets, as best I can. Maybe. There we go. And this would have a 1 minus charge, right? So when we draw these polyatomic ions, we should always bracket them and then put their charge outside those brackets. So here's the nitrate. This is the correct structure. If we look at formal charge again, the 2 oxygens, the top one and the left one here, have a -1 formal charge. The oxygen on the bottom right has a 0 formal charge, and the nitrogen in the middle has a 1 plus formal charge. So it's really 1 minus, 1 plus, 1 minus, 0. In total, it is a 1 minus charge, which is good. That does need to match still. But we kind of have these formal charges all over the place. But here's why this is okay. In this molecule, we have something that's called resonance. Okay? If you look at these oxygens, what makes one of these oxygens different from the other? And the answer is nothing. So then it comes down to, well, where do you want to put this double bond? Should I put the double bond where I did, on the right side? Could it have been on top instead? Could it have been on the left instead? And the answer is sure, it could be in any of those 3 places. There's no difference between this oxygen and that oxygen and this oxygen. So where the double bond goes is kind of a weird question to ask because none of these are any better than the others. And the answer to that is that the double bond can go in any of those spots. And as a matter of fact, it sort of kind of exists in all of those spots because these oxygens are all equivalent. That double bond could be in any one of these spots at any given time. And that is called resonance. Okay, so here that was the question I was asking down here, right? Where do you want to put the double bond? And it can kind of go in any of those spots and it would be a-okay. All right, so resonance exists when there are equivalent structures for the same molecule. Essentially because no one structure is better than the others, these molecules resonate between all of the structures. When a molecule has resonance structures, it helps stabilize it. More resonance generally leads to more stability. So even though this molecule didn't minimize its formal charge, right? We have a 1 minus, a 1 plus, and a 1 minus. Even though that's not the best when it comes to formal charge, again, the goal is to get down to 0. It's okay because this has resonance. And again, resonance is going to be structures or multiple structures that show the exact same thing, and essentially it's going to be a double bond moving to a different location or a double bond moving to a different location. And resonance adds stability. So let's try and draw out the three of these, okay? So let's draw the three resonance structures for NO3. I'm going to pause my video and work on these and draw them out so it can go a little quicker here. But if you want to try pausing it and doing it yourself, go for it. But yeah, I'll be back in just a sec. All right, so these are the three resonance structures of our nitrate, okay? We have a double bond on the left side, we've moved it over to the right side, we've moved it up to the top. Again, if you look at these three structures, there's no difference, right? All that's changing is the double bonds in a different spot. But in terms of like the total number of electrons, in terms of the total number of double bonds and single bonds, in terms of like, you know, how many oxygens are singly bonded, how many oxygens are doubly bonded, they're all the same, right? And this is our resonance. Now, let's see if I can do this here. Perfect. When you draw resonance structures, we actually have to draw these double arrows in between the structures. And these are called resonance arrows. They're effectively showing us that, hey, this structure is the same as this structure, and this structure is the same as that structure, and they're all the same, right? And again, why does resonance occur, or when does resonance occur? Resonance happens when in your Lewis diagram, there's an equivalence choice, right? We got to a point where it's like, okay, we need a double bond, one double bond. Where should that go? And the answer is well, it can go in any of the spots, and all three of the spots are equally good. And that gives us three different types or three different resonance structures as a result. All right, so I've got two more of these problems, all right? We're going to do resonance structures for sulfate. We're going to do resonance structures for phosphate. I know these are two polyatomic ions again, right? First things first, we need a Lewis diagram. And at some point in the Lewis diagram, we're going to end up at a spot where there's choices. There's a choice where we want to put double bonds. And there isn't necessarily a correct answer, and there's multiple structures or multiple ways of doing it that could exist. So if you want to try these by yourself, I would recommend that you do. Your homework, which is due tomorrow night, is going to be related to these as well. There's a couple of these at the bottom of your homework. Sorry, I'm going to take a sip of coffee. That's good stuff. All right. So give this a shot if you could, and I'll come back in just a second, go through a couple things with you, and you know, help you analyze this, and then I'll draw out all these structures for you guys and make sure that we have the correct answers. All right, so here's how far I've gotten, and then I'll kind of talk you through where I'm at right now. So again, we want to draw a Lewis diagram, right? We use the same rules as always. So the first rule is, hey, how many valence electrons do we have? Well, sulfur has 6, oxygen has 6, so 5 times 6 is 30. Plus, we have 2 negative charge, which means we've gained a couple electrons. So we have 32 to go, or 32 to add, right? Sulfur's in the middle. We start there. I add the 4 oxygens around the outside. I need at least one bond between them all. That took 8 electrons. I have 24 left to add, and I add those to the outside. 6, 12, 18, 24. They're all on the structure. So we're good. I'm going to get rid of this, just because, again, that math is been done a whole bunch of times, so I hope that makes sense to you. But anyway, so here's where I'm at. If I check my formal charges, okay, we're going to see that the oxygens, which the oxygens are around the outside, right? So formal charge for the oxygens is going to be 6 valence electrons minus 7 dots and dashes. Every single one of my oxygens currently is a -1. The sulfur in the middle, which is 6 valence electrons minus 4 dots and dashes. The sulfur is currently a 2+. So it's not great. We can fix this. We can make this better. We can get more of these formal charges closer to 0, right? 1 minus, 1 minus, 1 minus, 1 minus, 2+. That's not the best. We can do better. So let's start making a double bond or two. All right. I'm going to take, well, let me ask you this. Which oxygen do you want to make a double bond for? I don't know. It doesn't matter, right? They're all kind of the same. So I'll start at the top, I guess. I'll get rid of that lone pair. Make a second bond. Okay. And now let's look at the formal charge. So now I have, for the sulfur in the middle, I have 6 valence electrons, minus 1, 2, 3, 4, 5 dashes is still a 1+. This oxygen is now 0. 6 valence electrons minus 1, 2, 3, 4, 5, 6 dots and dashes for 0. These 3 are still 1-. Okay? And that's okay. But we can do better yet. I think we can add a second bond to this to get more formal charges down to 0. So let's do it. Where do you want the second double bond to go? I don't know. It doesn't matter, right? It really doesn't matter because they're all the same. So let me just do it on the right one, I guess. That'll work. And there we go. Let's check formal charge one last time. Sulfur in the middle. 6 valence electrons minus 6 dashes. Awesome. That's good. 0. This one. These two oxygens, right, with the double bonds. 6 valence electrons minus 1, 2, 3, 4, 5, 6. Dots and dashes. Perfect. These two oxygens. 6 valence electrons minus 1, 2, 3, 4, 5, 6, 7. Dots and dashes. This oxygen's a minus 1. This oxygen's a minus 1. But we need minus charges, right? We need negative charges in the structure. It's still a 2 minus polyatomic ion. So if I tried to make a third double bond, okay, what ends up happening is I end up getting a negative charge on my sulfur. Now, this is an old rule, or it's a rule in 2.5 that we haven't really discussed yet, but it is in there. There's a rule that says that we want to have negative charges on more electronegative elements. So oxygen is more electronegative than sulfur. So in theory, it looks like we could maybe add another double bond here, and that would make this oxygen 0, but all that would really do is shift our -1 charge from this oxygen to the sulfur. And because oxygen is more electronegative, we'd actually like to keep it outside. We'd like to keep it on the oxygen instead of the sulfur, because this actually wants electrons more. So this can sort of hold a 1- formal charge more comfortably than the sulfur can. So we've made a double bond to get this oxygen to 0. We've made another double bond to get this oxygen to 0. And as a result, we've also made the sulfur 0. But we still have 2 -1s out here, and that's okay, because that's as good as we can do, because we still have a 2- charge overall. All right, so now it leads us to this, right? We have one structure of the sulfate with 2 double bonds in the top and into the right. Do they have to be up and to the right? Of course not. They could be in other places. I could have one that's up and down. I could have one that's up and left. I could have one that's right and down. I could have one that's right and left. I could have one that's down and left. There are 6 resonance structures for this Lewis diagram. I'm going to pause the video and draw all of those out. You're more than welcome to do this as well. Yeah, I'll be back in just a bit. All right, so this is what it should all look like when it's all done, okay? We have 6 structures, right? We figured out that the two oxygens double bonded, 2 oxygens single bonded for sulfate is the best structure using the formal charge. But where these double bonds go, we have choices, right? All of the oxygens are essentially the same thing, and we can move these any which way. So I've got up and to the right, up and to the left, right, down and to the right, down and to the left, up and down, and then, sorry, my face is in the way here, left and right. All of these are resonance structures of one another. These are all appropriate Lewis diagrams for sulfate. And I have these double arrows between, like, a couple of these. In reality, you could have double arrows, like, between any of these, right? These are all essentially equivalent. They're all equal. And that's what resonance is, okay? I hope that makes sense. We do have one more on phosphate right here. Try it. Please try it. I'm going to just give you the answer in a little bit here. And yeah, I'll just reveal the answer. And then your homework again is due tomorrow night at Thursday. I hope I'm back at school tomorrow. That would make my life much easier, and I'm sure your life much easier. But anyway, yeah, so let me draw out all these structures for you. I'll show you the answers, and then we'll call it a day. All right, so I've got one structure done for you. Now, I just want to recap and make sure that we're all on the same page and that we get the exact same, starting point before we start doing our resonance. So we have in this molecule phosphorus, which is 5 valence electrons, 4 oxygens, which is another 24, because there's 6 valence electrons each. So 5 plus 24 is 29. 3- charge gives us 3 more, we're up to 32. We would need to put phosphorus in the middle and make 1 bond to each oxygen. -8 would get us down to 24. We'd add the rest around the outside, and all of our electrons have been added. At that point in time, again, we're looking at formal charge, right? If all 4 oxygens were single bonded, we would have 1-, 1-, 1-, 1-, and phosphorus would be 1+. We can minimize formal charge a little bit. If I make one double bond between one oxygen and phosphorus, that'll drop the formal charge of the phosphorus down to 0, and it'll drop the formal charge of that doubly bonded oxygen down to 0. Okay, the other 3 oxygens are all going to be -1, -1, -1. But our polyatomic ion has a 3- charge, so it is what it is. They need to go somewhere, right? Now, if we made a second double bond, it would be the same situation that we would try to do with sulfate, right? If I make a second double bond, I'm changing this formal charge of oxygen to 0. But I'm making this formal charge of phosphorus -1, or 1-. That's not great. I would rather have the 1- charge on the more electronegative element, oxygen, than I would on the less electronegative element, phosphorus. So instead of making 2 double bonds, 3 double bonds, or whatever, we want to keep the formal charges of -1 on the more electronegative elements, which is oxygen. So this is one structure. This is an appropriate structure. Formal charge is 0 up top, 0 in the middle, -1, -1, -1. Does that double bond need to go up top? Of course not. It can go in any of the 4 spots. I'll draw out the other 4, and then I'll show you those answers, and then we'll be all done. All right, so here's my 4 resonance structures for phosphate. Again, all I'm doing is moving the double bond, right? Same number of electrons, same number of single bonds, same number of double bonds. It's just where the double bond shows up. So I have up, down, left, right. Those are the 4 options. This has 4 resonance structures. Okay, so I'm all done. Please have a lovely day. If you need any help, I will be in my office hours, so I'm not like completely bailing on the day. I'm working from home. But yeah, your homework topic 2 is due tomorrow night by midnight, and we will catch you guys tomorrow. See you later.